For nearly 40 years, everything we thought we knew about Uranus may have been wrong. Not because scientists made a mistake, but because of terrible timing. In 1986, Voyager 2 performed the only close flyby of Uranus humanity has ever achieved. During that brief encounter, the spacecraft detected something shocking. Radiation levels so extreme they shouldn't have existed at all. The data suggested Uranus was wrapped in a violently intense radiation environment, far more dangerous than expected. That single moment reshaped decades of planetary science. But now, new research suggests something unsettling. Voyager 2 may not have seen Uranus as it truly is. Instead, it may have arrived at the absolute worst possible moment, during a rare cosmic disturbance that temporarily supercharged the planet's radiation belts. If that's true, then 40 years of assumptions may be built on a coincidence. So what exactly did Voyager see? How did scientists finally figure it out? And what else in the universe might we be misunderstanding because of bad timing? When Voyager 2 reached Uranus on January 24th, 1986, scientists expected something fairly modest. Uranus is an ice giant with a relatively weak plasma environment. Compared to planets like Jupiter, there simply shouldn't have been enough charged material to generate extreme radiation. But the data didn't just challenge expectations, it completely shattered them. Voyager's instruments detected electron radiation levels far higher than any existing model could explain. Energetic particles were trapped in Uranus's magnetic environment at intensities that made no physical sense. The radiation belts appeared dangerously strong despite the fact that very little plasma, the raw material needed to energize those belts, was present. For decades, this result haunted planetary scientists. A planet's magnetosphere acts like a magnetic bubble, trapping charged particles and shaping how it interacts with space weather. At Earth, radiation belts intensify when solar wind disturbances inject energy into the system, often during geomagnetic storms. But when Voyager measured Uranus, there was no obvious mechanism capable of producing such extreme radiation. Even Uranus's bizarre magnetic field, tilted nearly 60 degrees from its rotation axis and offset from the planet's center, didn't fully explain what Voyager saw. The numbers were simply too high. As a result, Uranus gained a reputation as a planetary outlier, a world governed by unfamiliar physics, behaving in ways no other magnetosphere did. And because Voyager 2 remains the only spacecraft ever to visit Uranus, there was no second data point to challenge that interpretation. So the mystery remained frozen in time, but everything hinged on one silent assumption: that Voyager 2 observed Uranus in its normal state. What if that assumption was wrong? The breakthrough came when scientists re-examined Voyager's data using something researchers in 1986 didn't yet fully understand: space weather. A team at the Southwest Research Institute realized that Voyager 2 may have crossed Uranus during a rare and powerful solar wind structure known as a co-rotating interaction region, or CIR. CIRs form when fast streams of solar wind catch up to slower ones, creating compressed walls of charged particles and intense magnetic turbulence. These structures propagate through the solar system like invisible shock waves. At Earth, CIRs are known to be dangerous. They can rapidly accelerate electrons to extreme energies, supercharging radiation belts and triggering geomagnetic storms. In 2019, one such event dramatically intensified Earth's radiation environment, proving these structures are anything but subtle. When scientists compared those Earth-based events with Voyager's Uranus data, the similarities were impossible to ignore. Voyager detected some of the most intense high-frequency plasma waves of its entire mission. These waves were far stronger than what would normally exist in quiet interplanetary space. And today, we know something critical that wasn't clear in the 1980s. Under the right conditions, these waves don't just scatter particles, they accelerate them. Suddenly, the puzzle clicked into place. If a co-rotating interaction region slammed into Uranus at just the wrong moment, it could have temporarily flooded the magnetosphere with energy. The radiation belts wouldn't reflect Uranus's usual environment. They would represent a cosmic perfect storm, captured during its peak intensity. Voyager didn't find a permanently extreme planet. It caught Uranus in the middle of a solar wind onslaught. This discovery doesn't just solve an old mystery, it forces scientists to rethink decades of assumptions. If Voyager arrived during an event that occurs less than 5% of the time, then our only direct measurement of Uranus may be fundamentally misleading. The planet long considered one of the solar system's strangest worlds might actually be far more ordinary and far more dynamic than we believed. That matters because Uranus isn't just one planet. Across the galaxy, astronomers have discovered thousands of exoplanets similar in size and composition to Uranus. Ice giants may be among the most common types of planets in the universe. If our understanding of Uranus is skewed, then our interpretation of countless distant worlds could be skewed as well. This revelation also strengthens the case for a dedicated Uranus mission. A single flyby, especially one conducted during extreme space weather, can't capture the true nature of a planetary system. Scientists now argue that only an orbiter, observing Uranus over long periods of time, can reveal both its calm baseline state and how it reacts to solar disturbances. And the implications don't stop there. If transient solar wind events can dramatically alter radiation environments at Uranus, the same may be true for Neptune and other distant worlds. Even the radiation conditions surrounding their moons, environments tied to habitability and surface chemistry, may be more variable than we once thought. This research tells a deeper story about how science evolves. Voyager's data was never wrong. It was simply interpreted through the limits of 1980s knowledge. With decades of new understanding about space weather and magnetospheric physics, scientists can now return to old data and uncover truths that were invisible at the time. Voyager 2 didn't discover a radiation monster. It captured a rare moment, a snapshot of Uranus at its most extreme, shaped by forces sweeping through the solar system. That raises a powerful question. If Uranus's reputation was shaped by bad timing, what else in the universe do we think we understand simply because we've only seen it once? If Voyager had arrived days earlier or later, Uranus might be viewed as a completely different planet today. So what do you think? Was Uranus ever truly extreme? Or did Voyager just arrive at the worst possible moment? Let me know your thoughts in the comments. If you enjoyed this video, don't forget to like, share, and subscribe for more updates on space exploration and scientific discoveries. Your support truly makes a difference and helps this channel grow. Thank you for watching, and see you next time.